Welcome to video course on system identification. I'm Dr. Ria Asmitha, working as the assistant professor in the Department of Electronics and Instrumentation Engineering, SRM Institute of Science and Technology, Kattangulattur. These are the course contents for this video course. First, we are going to see what is system identification. What is the introduction to system identification? What are the different types of dynamic systems that is used for system identification? There are various methods we have for identifying the system identification in dynamic systems. Next comes the types of model. What are the various types of models in discrete time systems? And what are the procedure for identifying the system? And what are the different methods to find the system identification? And then finally, we have the non-linearities. So first, let us move to the introduction. System identification is nothing but we are extracting the information about the system from the measured input and the output data. You have one input data and you have an output data of any system. From the system, get the input data and collect the output data and input both the input and the output data to system identification and search and you select some of the models whatever is needed to identify the particular system and then obtain the model. So this is this we call it as system identification. So this is also used to identify the controllability matrix and observability matrix. So for if there is any sensor issues or if you want to measure anything, then we can convert those things into a matrix. And also to detect the actuator and sensor failure. What is system identification? So it is nothing but process of creating a model of dynamic system using the measured data. So here can you see the diagram? So this is your input signal and this is the output signal. So these input and the output signal can be taken from the any systems. For example, if you take a distillation column, you can get the input data and collect the output data. From the using those input and the output data, you have to import to the system identification toolboxes. After importing, select the model. So we have various models like ARMA model, then ARX model, then moving average model. So those models you can apply. So we'll see all those things in the next coming videos. So after applying all these things, you will get one model. So that we call it as the system identification. So once the model is created, the next one is you have to use the controller design to tune a controllers using the Ziegler-Nichols open loop method or the closed loop method to find the performance of the simulation of the any process or the system. So next comes the model. So what do you mean by model? So model is nothing but description of any system. For example, if you take a liquid level control, liquid level system. So in liquid level system, you have an input and you have the output. So water is flowing to the tank and the water is coming or draining out. So for this liquid system, you have to first you have to use the mass balance equation to develop the mathematical model by obtaining the differential equation. So once you get the differential equation and then apply Laplace transform and find the transfer function, that is output of the system to the input of the system. So that gives the transfer function, which is nothing but the mathematical model. So similarly, there are various models we have. We have studied about this mathematical model in the process control. So now here we have three different types of models. One is the mental model or the verbal model, and second one is the graphical model, and third one is the mathematical model. So verbal model is nothing but it is a you don't have any mathematical formula. There is no mathematical relations. So just whatever we have as a sentence or as a word we can use as a model. See here we have an example. Turning the wheel causes the car to turn. So this is one sentence. It's a verbal sentence. So that means you can understand the meaning of that. So we are going to turning the wheel by using the by making the car to turn. So that this is so the sentence that gives a meaning without any mathematical solutions. So that we call it as a mental model. And next one is the graphical model. So graphical model is nothing but we have done some, we have studied about the frequency response analysis and time response analysis. For frequency and time domain, we have used the root locus control for time, and for frequency, we have used Bode plot. So from the Bode plot, you will get some responses. So from the responses or from the time domain analysis, we can easily find, if you take a time analysis, you can find what is the rise time, peak time, then what is the settling time, how much error you have. All these things you can calculate from the simulation results. Similarly, for the frequency response, you have two types of plots. One for the magnitude plot, another one is the phase plot. So using those magnitude and the phase plot, we can easily obtain the, we can check whether the system is stable or unstable, or we can find, can analyze the gain margin, phase margin, then gain crossover and phase crossover. So this is the another model that is nothing but the graphical model. And third one is the mathematical model. So in the mathematical model, first you have to, based on the conditions, we have to develop the mathematical model, develop the differential equations. Using those equations, you have to find the model. So that gives the mathematical model. In graphical model, we are using some tables. For if you want to find the frequency analysis, then for magnitude plot, you are going to obtain the results, simulation results for frequency versus magnitude, then frequency versus phase angle. Similarly, for time domain analysis, you are going to find for time domain analysis, you have to find the time versus your amplitude. So this are the, from this you will obtain a model. So that model will be used for system identification. So this is the description of model. Model is nothing but description of things. I can say a description of any system. So we have three types of model. So this mental model is nothing but it does not involve any mathematical formula, or through our practical experience, through the knowledge we can get those model. So that is your mental model. Next one is the graphical model. So you have to using the tables and the plots will get with respect to time and with respect to frequency. And mathematical model, you have to develop the mathematical equations or differential equations like this. From the differential equation, we can easily convert that into a model. So here I have given one equation. So this is the differential equation. For the differential equation, apply Laplace transform. So they will give s square y of s and 2s y of s and plus y of s equal to 3 with in terms of all inputs. So combine all x of s and combine all y of s. So we will get a transfer function which is nothing but the output by the input. So y of s by x of s equal to, we'll get the transfer function. So this is one model that we obtained from the differential equation. The same equation we can convert into a difference equation. So then if you have d square x by dt square, which is nothing but a second order input equation, in second order can be easily converted into difference equation by representing y of n minus 2, which is equivalent to d square y by dt square, plus 2 y of n minus 1, which is equivalent to 2 dy by dt, and y of n is nothing but y of t, which is equal to 3 x of n minus 1 is nothing but 3 dx by dt plus 2 x of t. So here this is y of n minus 2 is nothing but a delay signal with the delay of two samples. So we can represent as z power minus 2. In time, in continuous can use Laplace transform, but in difference or in discrete, I have to use z transform for analysis. So I can convert this to z power minus 2, z power minus 1, y of z. So here also you have to combine all y of z and x of z. From this you find the transfer function y by x of z equal to this. So from this what we can understand is, for continuous system you have to find the model by equating output by input by applying a Laplace transform. But for discrete, you have to take z transform to find the transfer function. So here you have to represent it by y of z by x of z. So you will get one model. So any model can be developed using two ways. One is the mathematical modeling, that is what you have seen before. Another one is the model based on experimentation. So which is nothing but a system identification. So you have to get the input data, recorded input data, and recorded output data. From the input and the output recorded data, we can obtain the system identification models. So that is nothing but the model based on experimentation. So this is the definition for the system identification. So I can define a system identification as a study of modeling dynamic system from the experiment data. Experiment data is nothing but the recorded input and the recorded output. Then system identification procedure. So the first procedure is you have to collect the data. So you have to collect the data of any system. Data is nothing but your input data and the output data of any system. And then after collecting the input and the output data, the next one is you have to choose a model structure. So which model is suitable for that particular record input and the output. So if it is not satisfied, or if the model is not done up to that mark, or if it not gives an accurately detect the model, then we have to choose another structure and to find the system identification. And third one is choose system identification approach. There are different approaches we have for system identification. One is the open loop approach. Another one is the closed loop approach. So using in open loop approach, we can use some online or offline identification methods to identify the open loop approach. For closed loop approach, we can use some transient analysis or frequency analysis or correlation analysis to find the identification approach. And after obtaining the selecting the suitable identification approach, the next one is determine the best model. From those online and the offline, or both the open and the closed loop, you have to choose which is the best model. After finding the best model, we have to validate. So validate is nothing but you are just comparing with the real model and finding the error. That error has to be reduced by applying online and offline methods. So this is the procedure for system identification. So there are two approaches or two methods in system identification. One is the non-parametric method, and next one is the parametric method. So the non-parametric method is nothing but it gives only the basic information. So the basic information, which is nothing but it will give what is the gain of a system and how to find the time constant, then settling time, then delay time, rise time, peak time. All these are the basic informations that can be obtained after getting those informations. We can make it as a table and we can see the response. So that is the non-parametric. It gives only the basic information. Whereas the parametric method is nothing but it gives the value of the parameter in the model. So the results are the values of the parameter that provide accuracy. So in parametric methods, the results when compared to non-parametric method, the results are more accurate, and we can get the parameter in the model is nothing but we will have some parameter values. That values are very important for identification. The parameter model, it's very essential, or we have to choose those values properly to get the accurate model. So the next comes the model of linear time invariant system. There are three different models. One is the linear model, next one is the state space model, and next one is the output error model. So linear error model, we have to apply the linear theorem, which is nothing but applying the superposition principle. Superposition principle is nothing but the sum of the output of all the input is equal to sum of the output of individual input. We have to find the outputs of individual input and take the sum, which is equal to the overall outputs. So this we call it as the linear model. Once we check the linear model and after obtaining the linearity, you have to check for the linearity. After finding the linearity, then you have to get the apply Laplace transform to get the linear model. So here we have one example for checking the linear model. So this is the condition for this is the problem y equals 0 to n x of t minus k. So first you expand this and check the linearity. So I'm considering the first one is y1 of t and y2 of t. Then find what is y3 of t. After finding that, then find what is y4 of t and check whether both y3 and y4 are equal. If it is equal, then we can say that the system is linear. And after checking the linearity, then apply the Laplace transform for this and find what is y of s by x of s. Suppose if the equation is in terms of difference equation, this is the continuous one, but this is the discrete one. If it is in this case, then you have to find the, this is y of t plus 2, y of t minus 1, y of t minus 2. So you have to find the inverse. Okay, when you find the inverse, you will get y of s. Then 2, this is t minus 1 is the 1 delay. So 2s pi power minus 1 y of s, and find what is y by x. The next one is the straight space model. The transfer function always the initial current starts with 0, and it has some drawback. The first drawback is this can be defined only under initial condition is 0. And second one is it can be carried out or used for single input and single output system. Only for single input and single output we can use this transfer function model. And this transfer function model, it doesn't give the information about the internal behavior, what is happening inside internally of any system. That is the main drawback in transfer function model. This can be overcome by using a state space model. So before we are going to in state space model, we can it is not necessary you have to use only for the initial conditions. We can use it for multi-input and multi-output system. And the internal behavior of the system can be understood with the help of this state space model by assigning each thing as one state variable. That we will see one by one now. This is the state space formulation. One is the state, which is nothing but minimum set of variables completely determine the behavior of the system. So if you have a continuous, I'm having on continuous stirred tank reactor. In continuous stirred tank reactor, so you have two concentration of liquids are flowing into the tank, and it will have to mix it thoroughly. After mixed thoroughly, then we have to get the mixture. So for that, I'm sending one concentration of liquid and then concentration of liquid B. So when you are sending the concentration of liquid, you have to control the flow. So I have to control the flow of the liquid and flow of the concentration B. Once it's get into the tank, I have to maintain the level of the tank, and then it has to mix it properly. So we have to maintain the temperature. So there we have various different controls we need to apply in this. So after getting all these things, we need to control each. And so each one of the control I'm considering as one state variable. X1 as state variable for the flow A, and flow B as another, and flow C is the level of the tank and temperature. Like that we have 4 levels. Flow I can consider. So if there is any problem, in any one of the variables, that variable alone we can find it and we can replace. If there is any sensor issue in any of the control, then that particular will be considered as one state variables. So that can be easily replaced and we can easily identify where the fault is. The next one is the state vector. So state vector is nothing but the vector of n state variables describe the behavior of the system. So how the system behaves. So in that we are taking n number of state variables. So each variable will give the behavior of the system. Suppose if we have 5 state variables, then we can represent it as x1, x2, x3, x4. If you consider the same CSTR example, there I want to control four parameters. So I'm considering each four one as one for the flow, another for the flow of the concentration B, and the third state variable as the temperature, how much, and then fourth variable I have to consider as a level. So like that I can consider all four state variables. All the four state, if I put it as a matrix, then we call that as a state vector. And next comes the state equation. State equation is nothing but the first order derivative of the state variables, and the input is called the state equation. The first order derivative is nothing but take the differential equation, first order equation, that is nothing but dx by dt. So that can be represented as x1 dot, which is equal to dx by dt, x1 plus x2 plus x3. These are all some of the state variables, and you have the input. So state equation always it has the state variables, and it's a combination of state variables and the input, that we call it as state equation. The state model is nothing but the state equation and the output equation together, we call it as state model. So the state model has the state equation, which is nothing but the first order derivative, and next one is the output equation, y equation. This combined together we call it as state model. So I can represent it as x dot equal to ax plus bu, where A is the system matrix and B is your input matrix. And similarly, we can represent the output equation Y. Let's see one problem. Consider the state model of the system given by the differential equation. So here I have one differential equation, that is d square by dt square plus 6 d square y by dt square minus 10 dy by dt plus 7y equal to 0. So now I have to assume the state variables. So to assume the state variables, first I'm considering y equal to x1, because this equation it has the variable y. So I'm taking this y is equal to x1. I'm just converting this entire equation into a first order derivative with state variables. Then differentiating with respect to t, you will get, I'm considering that as x2. Then one more differentiation of this second one, you will get it as x3. Then I'm considering, because this equation is a third order equation, so I have to find up to d cube y by dt cube. So when you take d cube y by dt cube, no need to take it as x4. That will give us more of state variables, and we need only the first order derivative. So instead of that, I'm just taking the derivative for this x3 dot. When I take the derivative of x3 dot, which is equal to d cube y by dt square, so I can avoid one state variables, and also I can easily convert into a one first order derivative of any of the state variables. So these are the conditions we have to assume. After getting all these three, then substitute in this equation. So then now the equation becomes x3 dot d cube y by dt cube is nothing but x3 dot, and this is x3. So minus 6x3, then minus 10x2 plus 7x1 plus u equal to 0. From this you find what is x3 dot. Now you have to, what are the next two you need to find? You have to find x1 dot and x2 dot. So how to get this x1 dot? X1 dot is nothing. If you take one derivative x1 dot, this becomes dy by dt, which is equal to x2. So I'm taking x1 dot equal to x2. Similarly, find x2 dot. If you put x2 dot, this becomes one more derivative. So d square y by dt square, which is equal to x3. So it is equal to x3. So now you have three state variables and three first order equation, first order derivative, which is nothing but x1 dot, x2 dot, x3 dot. So that is the equation. From this, find this matrix. This is the system matrix, and this is the input matrix. So from next, find the output equation, which is equal to y equal to x1. And since you have three state variables, I can represent it as 1, 0, 0 into x1, x2 and x3. So this is how you have to get the state model from the differential equations. The same way you can get for the discrete equation. So for discrete equation, you'll have a difference equations. So this is the difference equation. For this difference equations, you have to apply the transform. This is k plus 2 is advanced function, so make it as z square and this is all or in terms of plus. Okay, so you make it as z. All the powers of z will be in as positive. Then find what is y by u. After finding this y by u, you have to apply partial fractions. That is 1 by z plus 2, 1 by z plus 3. Find a by z plus 2, a b by z plus 3. And find the value of a and b. So when you find the values of a and b, you will get 1 and minus 1. Then after finding this a and b value, substitute in this equation. So you will get 1 by z plus 2 minus 1 by z plus 3. Bring this u of z to that side. So this is the equation you will get. After this, I am just going to convert this into 1 by z, 1 plus, I'm taking this z term outside. And so you will get 1 plus 2 z inverse. And this becomes 1 plus 3 z power minus 1. So now this is of the form g divided by 1 plus gh. So it's nothing but a closed loop transfer function. And similarly, this is g divided by 1 plus gh, where g is your z power minus 1 and h is your feedback is 3. So using these conditions, I am going to draw a block diagram. So now the first equation is u of z. So draw input equation u of z. Then all our additions, so put a summa here, because this equation is nothing but a closed loop transfer. Closed loop transfer function, you have a summa with g and h. So this is g is z inverse, h is 2. So draw the one block diagram. And for this case, you have to draw another block diagram, z power minus 1 and 3, and combine these two. Now, so this is multiplied with 1 and minus 1. So this is 1, so put 1 here. This is minus 1, so put minus 1, combine together, you will get this transfer function. So this is the block diagram. Now, from the block diagram, you have to obtain the model. How to get the model? Now, whenever you have a z inverse, if you take the derivative of that z inverse, you will get x2, right? So here I'm taking this is x1 of k plus 1, the first order derivative. With the one delay, you will get x2. Similarly, here I'm considering this input as second or first order derivative, x2 of k plus 1. With one delay, you will get the output as x2. So from this, you can easily get the model. So in a differential equation, you have to represent the first order derivative as x dot. Here you have to make it as x of k plus 1. The k plus 1 represents the first order. If you put k plus 2, that represents second order. So I can write this as x1 of k plus 1 and this is x2 of k plus 1. This x1 of k plus 1 is nothing. What is this x1 of k plus 1? What are the inputs connected to this x1 of k plus 1? This is u of z. And here, this connection. This connection is nothing but we have 2 and this is x2, which is connected to a negative sign. So I can write it as minus 2x. This is x1, minus 2x1. That's why you will get as minus 2x1. Similarly, for this case, x2 of k plus 1, again the same u is coming, one connection. Another one is this is, these two are added to give x2 of k plus 1. So this is connected to minus sign with 3 and x2. So this is minus 3 x2. And what is y? Y is nothing but this input and this input. So this input is nothing but x1 into 1, then minus of x2, minus of x2. So x1 minus x2. So after getting the equations, you have to form a matrix. This is the matrix. This is x1 of k plus 1, x2 of k plus 1. This is minus 2, minus 3. And also find what is the equation for the output. That is 1 minus 1. Here you have only two state variables. So it is x1 and x2. Similarly, you have to do the problem by using this 10 by z into z plus 1, z plus 2. Apply a partial fraction. And from the partial fraction, you have to make it as a closed loop transfer function g by 1 plus gh. So after that, you have to, after getting the transfer function, then draw the block diagram. And since you have three values, then you have three state variables and three first order equations. So you have to find x1 of k plus 1, x2 of k plus 1 and x3 of k plus 1, and state variables are x1, x2 and x3. So like this you will get from this find what is x1, x2 and x3 of k plus 1 and get the model. So model is nothing but the equation and the output equation combined together, we call it as state model. So next comes the output error model. So we call it as an OE model. So this model, there are two types of output error model. One is the deterministic model, another one is stochastic model. So deterministic model is nothing but we can easily predict the output. When I give a step input to any system, if it is an open loop system, I know very well that the output is always a sigmoidal shape. If I give a step input to a second order system, I know that you will have an oscillations and overdamp and underdamp will be there. So and finally it will settle. It depends on the time, how much it takes. So we can predict the output when an input is given to a system. So that we call it as a deterministic model. The stochastic model is we cannot predict the output. So whenever a disturbance comes, we do not know at what time the disturbance will come and how it affects the system or how the noise affects the system. So that we call it as stochastic system. So this output error, this is the general model equation which is represented by A of q, y of t equal to B of q by f of q. This is the general equation. So this has one system delay. This t minus k is nothing but the system delay, and this is the system disturbance, or we call it as an error. The same equation we can convert into a discrete system. Wherever you have t, that replace it by k. So a of z and q will be represented by z because here we are using a z transform. So y of k, b of z by f of z, a of k minus n, c by d, then e of k. So this you can draw as a model structure. So model structure is nothing but what you have to use this b by f of z is have a unit, input with all delays, all delayed inputs, and c by d is nothing but the error. So this is this equation, c by d into error. This is added with all the inputs of coefficient of parameter b by f. This is b by f. This together we call it as the model structure for this system. So output error model for continuous system we can consider as b by f of q, b by f into e of t minus k, and e of t. So CD you have to take it as ACD, you have to take it as 1. So this is what is explained here. Deterministic model where the model parameters are known and assume. This model describes the behavior of the system on the basis of the physical laws. So we have to apply some laws to get this. But stochastic model is the one where the model parameters are predicted or taken randomly. So in output error model, in the basic general equations, you have to make the polynomial a, c, d as 1. If you make this a, c, d equal to 1, then we call that model as output error model. So now the equation becomes wherever you have this ACD, that ACD if you make it as 1, then you will get only B by F plus E of t. So that gives the output error model. So next comes the non-linearity. So non-linearity, whenever when an input is given to a system, if the system, for the bounded input, if you get a bounded output, we call it as stable system, and also we can say the system is a linear. For non-linear case, the system keep on changing, so that because of that the output, it will not be stabilized. So such things we call it as a non-linear. So the non-linear, there are different types of non-linearities present in the system. One is the saturation non-linearity. Another one is dead zone non-linearity, friction, backlash, and stiffness. So when input is given to a system, and if the output is similar and the magnitude is proportional to the input, then the system is linear. When the step input is given to a system, if the output is not similar, that means its magnitude keeps on increasing, then we say that the system is non-linear. So these are some of the non-linearities present in the system. The first one is the saturation non-linearity. Here in saturation non-linearity, the output, see that this is the input and this is the output. Output is proportional to a certain range. Only for up to this range, it is both the input and the output are linear. Afterwards, it remains constant. So this we call it as saturation nonlinearity. So this is the input-output relationship of saturation nonlinearity. And dead zone is, so it will, if you take the input and the output for a particular period, it remains dead. And then it starts, the input starts responding so that you will get an output. So this we call it as a dead zone. And next one is the Z dead zone and the nonlinearity. So this region, up to this region we call it as dead zone, and up to this second part we call it as a saturation. It has both dead zone as well as the saturation. And friction is nothing but when there is a relative motion between the contacting surfaces. If you have a relative motion, two surfaces if you're contacting, then a nonlinearity exists. So there are two types. One is the viscous friction nonlinearity and Coulomb friction nonlinearity. In viscous friction nonlinearity, you have a constant, keeps on increasing. When input is given to a system, it keeps on input and both are related and it keeps on increasing. There is no stabilized. And similarly for Coulomb, it increases over particular time and it is not a constant value. It's keep on increasing in exponentially increasing. Next, so what are the models that is models with nonlinearity? What are the models that's used in for nonlinearity? One is the Hammerstein model, another one is the Wiener model. So Hammerstein model is nothing but a model with static nonlinearity of the input is called a Hammerstein model. So this is the static nonlinearity, and this is your a model. So S1 is your nonlinearity, and S2 is your model. If you have a static nonlinearity, then we call that as Hammerstein model. So in Wiener model, first you will have S2 is a static nonlinearity and S1 is your linear model. Just the reverse case in the for the previous model, Hammerstein model. So the S2 is nothing but nonlinearity and S1 is the nonlinearity and S2 is your linear model. So here first comes the nonlinearity and here second comes the nonlinearity. So that we call it as the Wiener model. So if you have both Wiener as well as the Wiener and Hammerstein, then we call it as Hammerstein-Wiener model. Hammerstein. So in Hammerstein S1 and S3. The first one is the Hammerstein. So initially you will have the nonlinearity. And after the model, you will have the nonlinearity for the Vienna. That's why you have the linear model is in between, and this S1 is the nonlinearity. So that we call it this together, we call it as Hammerstein. This together, we call it as the Vienna. That's why this model is called as Hammerstein-Vienna model. So next comes the fuzzy model. So fuzzy model is nothing but a fuzzy relation that forms an algorithm for determining the output of any system. We can obtain the output of any system from finite number to past input and the output. So that such models we call it as fuzzy model. And the black box model, it is a model in which it can be viewed in terms of input and the output without, we don't have any knowledge about it. So whenever a flight crashes, so immediately they will go and search for the black box, because all the data will be recorded in that black box, so that they can easily trace out what was happened in the while the flight was flying. So that can be easily identified with the help of this black box model. So that's all about this course on the introduction to system identification. So just a recap of the full course of this course. One is, the first you have seen what is the introduction to system identification. Then what are the different systems used in dynamic or static systems. And then what are the models that is used for linear system as well as for the non-linear system. And then what are the different approaches that is used for the system identification methods. I hope I hope you will understand the concept which is given in this video course. Let us meet you on the next video. Thank you.